Welcome to another monthly QuakeCoRE seminar series event. It's my pleasure this morning to introduce Andrew Stolte. Andrew is the research engineer as part of Technology Platform 2, which is associated with field testing and monitoring. And so it's my pleasure to introduce him. He's working closely with Liam Wotherspoon, who's just made a nice late entrance to hear me finish this introduction. So Andrew, will hand it over to you and look forward to hearing your presentation.
Thank you very much. Let me share my screen. So thank you all for joining me today. Can you all hear me and see my screen? Okay, perfect. Today I'm going to be talking about improving understanding of the sedimentary basins in New Zealand through regional site investigation studies. And I'm just going to update us on a few of the basins throughout the country. So a brief outline of my presentation is I'm going to talk about basin effects. Why do we care about them? So why do we actually care about basin effects? I'm then going to highlight the site characterization methods we use to sort these effects out in our sedimentary basins. And then I'll go through some of the regional site characterization studies that we've undertaken the past few years, focusing on 5 different sedimentary basins. So brief basin effects 101. Historically, we have looked at ground motions that have occurred on strong motion stations on rock sites. For example, here shown in the bottom left, the ground motions tend to be very high frequency and relatively short in duration. If you were to take the same earthquake and look at a recording on a soil site in a sedimentary basin, the ground motion changes a little bit. What happens is you tend to see amplification at longer periods, higher or lower frequencies, and the duration of the waves, or the duration of the shaking tends to be quite significant after the main event. So here on the left, you see the shaking's quite small after the main event, and here you see increased amplification and longer shaking after the main event itself. So what causes this? Well, the increased shaking in soft sedimentary basins happens mostly due to 3 parts. First, we have general soil side effects, where soft soils tend to amplify the ground motions at longer periods. You also have the entrapment of the seismic waves within the basin, so it starts to bounce off the basin edges. Also near these basin edges, we get the generation of localized surface waves. But perhaps an easier way to think about it is to think about a jelly bowl. So if we have this bowl that we fill up with our Nan's dessert, you see we have multiple layers, could be different soils. And if we were to shake the bottom of this bowl with our hand, we would see that the shaking is amplified at the top of the bowl. The jelly is going to keep sloshing back and forth within. Furthermore, if we just stop the shaking, the jelly will actually continue to vibrate for some time after we stop the shaking. So instead of just looking at ground recordings, let's try to actually understand why we're getting this increased shaking and characterize the soil so we can move forward and design buildings later on. So the easiest method to do this is to actually look at what's going on in the jelly bowl or in the ground. And so the most common testing methods that we use are called invasive testing methods. This is where we put an instrument into the ground beneath the ground surface and look at the material properties. There we go. These types of methods generally give us localized measurements of the material properties. We're looking at the properties near a borehole or near a conical probe. These methods, one thing that's nice about these methods is the data processing is relatively simple. The disadvantage is that the tests are actually quite expensive. If you want to have a very deep borehole to characterize a sedimentary basin, you might be looking at something 1 kilometer deep. And that's just something that generally doesn't happen for geotechnical engineering purposes. Boreholes already themselves for a geotechnical site, about 30 meters, is very rare in engineering practice. So the methods that are commonly used in geotechnical engineering are, well, again, boreholes. We have the cone penetration test, the flat plate dilatometer test, and the standard penetration test. And if you're more like me, interested in dynamic properties, we use seismic methods, where we put instruments down boreholes, in between 2 boreholes, or we add instrumentation to our CPTs, our DMTs, or our cross-hole tests. In the figure on the right here, we have what is called a direct push cross-hole test. We push these cones into the ground and try to pull out the shear wave velocity of the soils in between these cones. However, with this test, we can only go maybe 20 meters deep. And again, the thing I want to highlight is with these seismic geophysical methods, we're trying to get shear wave velocity, understand the stiffness of the soil. So we want to go deeper into sedimentary basins, and so we are forced to turn to something called non-invasive methods. In this case, we place instrumentation at the ground surface and try to understand the properties of the soil beneath. A disadvantage of these methods is we tend to spatially average the material properties of the soils at these sites. For example, here in the bottom right, we have what's called an MASW array. We place geophones in a linear array across the ground surface. And what happens is we're actually averaging the soil stiffness in our measurements underneath the entire length of the array. And as we get to larger and larger and larger arrays, sometimes as large as a kilometer in diameter, we're again averaging the material properties. A disadvantage of the non-invasive methods is we can't directly measure shear wave velocity. Instead, we have to do some data processing to pull it out. The methods that I'm going to actually talk about in this presentation are two. The first one is a little bit simpler, called the H/V method, where we get site period. And then I'm going to talk about the more complex methods, surface wave testing, where we are able to get shear wave velocity profiles in the end. So the first method is the horizontal vertical to spectral ratio method. It's also called HVSR or H/V, and I'll probably interchange them in this presentation as I speak. But the method is relatively simple. You take a broadband seismometer capable of recording three ground motions, three components, north, south, east, west, and vertical, and place it in the ground. We let it record what are called ambient vibrations. So the earth around us is shaking all of the time, from small earthquakes that we don't actually normally feel, to the ocean waves hitting the coast, winds generating surface waves as it travels across our plains. All of this creates what we call the ambient wave field. And we use these measurements, we look at how these waves travel across our site and try to infer the properties of the soil underneath. So we get three recordings, north, south, east, west, and vertical components. We do some fancy math to transform it into the frequency domain, which lets us tease out a few more details about the shaking. So we have three different Fourier amplitude spectra, two for the horizontal components, one for the vertical. And the last step is quite simple. We take these, average the two horizontal components and divide them by the vertical component, hence the H/V. And we get what's called an H/V curve. And typically, the peak that we get in an H/V curve, we associate with the fundamental frequency of vibration at a site. I'm actually going to switch and start talking about this in terms of period. So frequency and period are just inverses of each other, but engineers tend to like to think in terms of period instead. So we repeat this process for multiple time windows in our ambient recordings, and we get an H/V curve for our site. What's great about this test is we can place a sensor, test for maybe 2 hours, pick it up, move, and go to another site. So this lets us rapidly characterize a sedimentary basin. So what does this give us? These peaks in the H/V that we are interested in are usually associated with strong impedance contrasts. Here on the right, I have a site from Christchurch, and there's actually three impedance contrasts that we can see depending upon where we are in the basin. At low periods, these are near the ground surface, shallow impedance contrasts, for example, shown here in blue. And as we go to longer and longer periods, these are associated with deeper impedance contrasts, such as the bedrock in the Canterbury Plains. If we are able to distinguish this bedrock peak, we call this the fundamental side period of vibration. This is going to be the period of vibration where we perhaps see the most amplification from a ground motion. Why do we care about this fundamental site period? Well, it directly inputs into our New Zealand building code. In fact, the site classification between a site class C, which is a shallow soil site, versus a site class D, a deep soil site, is in part can be determined using this site period measurement. And this cutoff is at 0.6 seconds. Any site period larger than 0.6 seconds is the deep soil site. The other testing methods we use, we're interested in actually measuring the shear wave stiffness. We're interested in measuring the stiffness of the soil. And to do that, we're going to use surface wave methods. These methods are quite complex, but I'm going to briefly just talk about the three big steps that we have in the processing. The first thing we do is we collect data in the field. We put sensors in an array on the ground and look how waves travel across it. We then take this data and process it to develop what we call a Rayleigh wave dispersion curve. The surface waves travel at different velocities at different frequencies. However, that is not actually what we're interested in. We are interested in getting a shear wave velocity profile, a measurement of the soil stiffness with depth. And so the process, the tricky part with surface wave is we need to take a theoretical ground model that we generate ourselves. We calculate a theoretical dispersion curve and fit it to our experimental data. And so we end up generating millions of ground models that might fit our theoretical or our experimental data, and we pick out the best ones. So when I talk about shear wave velocity, or sorry, surface wave testing results, I'm going to show you a lot of shear wave velocity profiles that actually fit our experimental data. The more fun part is, for me, is the field testing. So the actual testing methods we use in the field are two different ones. We have active testing, also called MASW, where we are actually generating the waves ourselves. I take a sledgehammer and hit the ground very hard and generate the waves. These waves travel across a linear array of sensors. The active testing tends to generate high frequency waves, short wavelengths, and what that means for us is it lets us profile the near surface on the scale of tens of meters. If we want to get deeper, we need to rely again on these ambient vibrations. We don't quite know where the ambient vibrations are coming from, so we use sensors that are in 2D arrays and look at how the ambient vibrations travel across the two-dimensional array. The benefit of ambient vibrations is they tend to be lower frequency, corresponding to longer wavelengths, and what that means for us in the end is we can profile deeper, tens to thousands of meters beneath our sedimentary basins. So now I've talked about our site characterization methods, let's actually talk about our sedimentary basins in New Zealand. So as you can see from this image, I've highlighted several sedimentary basins, several different bowls of jelly throughout the country. And the one thing I'd really like to highlight is that most of these sedimentary basins tend to be in high populated areas. The Canterbury Basin, the Wellington Basin, the Auckland Basin, Hamilton is in the Waikato Basin. Places where people like to live tend to be on these flat places near water. And unfortunately, ground shaking is usually increased in these basins. So recent efforts have been to characterize these areas. Several of the most recent studies over the past 8 or so years following the Canterbury Earthquake sequence have been the basins we've focused on the past few years. I'm highlighting in orange. And I'm going to talk about a few of them in this presentation, specifically 5. But we can't really get started talking about earthquake engineering in New Zealand without, again, looking back at Canterbury and building upon the things we've done there. So first I'll highlight the Canterbury Sedimentary Basin. Following the earthquakes, there was a series of total of 24 deep shear wave velocity profiles that were developed from surface wave testing in the basin. 14 initially in Christchurch, and then 10 at strong motion stations out in the Canterbury Plains. And these are shown by the green squares in Christchurch and the blue circles in the Canterbury Plains. During the same time, we've had HRV testing, multiple studies that were combined with the surface wave studies and then things subsequent since. I'm going to talk about 154 HRV measurements in total, and 80 of these came from a paper by Liam Wotherspoon in 2015. And some of those points here are shown by the red crosses. So first I'll talk about the surface wave results, and I'm only going to focus on one site just to highlight what surface wave testing actually looks like. As I mentioned, surface wave testing doesn't give us a single shear wave velocity profile, rather it gives us a suite. In this case, there were 1,000 best profiles that were fit to our experimental data, and those are shown by the cloud of gray lines, squiggles going back and forth. And you can see we're actually going quite deep. The surface wave testing, we were hopefully able to resolve stuff down to as deep as 2 kilometers. Just for speaking terms, I'm going to highlight the red curve in the middle, and that represents a median shear wave velocity profile that is summarizing the 1,000 models below. And what I'd like to highlight about the Canterbury region, if you know anything about the local geology, we have a series of gravel deposits coming from the Canterbury Plains that are quite stiff, indicated by higher shear wave velocities. And then you have marine sediments that are deposited coming into like Christchurch, and they tend to be soft silts and sands. What's cool about the shear wave velocity profile is we can actually see where this interlayering is at this site. You have the stiff gravels with higher shear wave velocities, the softer sediments with lower shear wave velocities, and goes back and forth and back and forth. And here on the right, we have an idealized soil profile showing just this. A disadvantage, as I mentioned, of the surface wave testing methods is we tend to average the material properties beneath our arrays. So as we have very, very large arrays, we start to lose our ability to distinguish small layers at great depth. If we move to the right figure, you'll see that we have the soft sediments in the top, and then we have a just undifferentiated soil layer going from about 200 meters down to bedrock, which is marked by a sharp increase in the shear wave velocity from about 100,000 meters per second up to about 3,500 meters per second. Another thing I'd like to highlight is we're actually still relatively uncertain about the depth to bedrock. Here you'll see some of our shear wave velocity profiles are indicating at bedrock about 1,300 meters per second, and whereas some of our other profiles are indicating something closer to 1.8 kilometers below the ground surface. So what we've done with this data, or I should say Michael Deshane did with this data for his thesis, was he took the surface wave testing results from the 28 sites and tried to come up with representative shear wave velocity profiles for the Canterbury soils. So he divided it into three groups. We have the intrabedded sites where we have the silts close to the coast. And so for those soils, he has the intrabedded sandy soils. He then has the intrabedded gravelly soils from these sites and broke them apart. You'll see that with depth, we have shear wave velocity increasing due to confinement. But if you look at the left, the red curve is the soft, sandy soils relative to the gray, gravelly soils at these same sites. And then finally, he looked at the gravel sites. As we move further into the Canterbury Plains, the soils are dominated by these gravels, and the gravels alone are indicated by the green. What I'd like to highlight is, yes, the soft soils are less stiff than the gravels. But as I mentioned, with increasing depth, we start to lose our ability to actually differentiate between these materials. And so he then generated a composite Canterbury curve for very great depth. What's this do for us? Well, this lets us have an estimate of shear wave velocity or soil stiffness across the Canterbury Plains. So if we don't have any site-specific data, we could look at this data to give us an idea of what the soil shaking may be like. And now I'm going to hop into something that I've dealt with, the H/V data from the Canterbury Plains. As I briefly alluded to earlier, the Canterbury Basin, we can see three strong impedance contrasts. The shallowest is associated with the Rickerton gravels. These are the peaks I'm highlighting in blue here. The best example here is at Hagley Park, where we're only seeing the impedance contrast due to the soft Christchurch sand silt formation overlying the stiffer Rickerton gravels. If you're close to the Port Hills, which are associated with the Banks Peninsula volcanics, you can see a stiff impedance contrast associated there, and that tends to be in the middle range of our site periods, about 1 second. And then, of course, the steepest impedance contrast that we're going to see is associated with bedrock, and that's what we would see at the CACS site, where we have a site period of about 5 or 6 seconds. And then depending on where you are in Christchurch or the Canterbury Plains as a whole, you're going to see a mixed combination of these peaks. So at Redwood Park, we see the gravels and we see the bedrock. At Garrett Park, we see the gravels and we see the Banks Peninsula volcanics, but we can't quite pull out a peak from the basement rock. And then at this Fitzgerald site, we actually see all three. So then rather than just staring at these H/V curves, we can start to look at what these site period trends in these site periods across the basin as a whole. So here's a map of the Canterbury Sedimentary Basin with Christchurch shown here in the middle of the figure. The gray is outlining the Banks Peninsula volcanics, and then the Alps are here to the northwest. What I'm showing here are colored dots of site period, where color is indicating the site period itself. Blue colors indicate small, short site periods, indicating a shallow soil site. And then the red colors indicate a deep site period, large numbers. For about 6.5 was the maximum we were seeing in this sedimentary basin. And what I'd like to highlight is, as expected, near the Alps, near the rock outcrops, the site period is quite low. In the middle of the sedimentary basin, we get something that's quite deep. Site period is again about 6.5. As we get closer to the Port Hills, the bedrock starts to shallow, and we get site periods around 3 to 4 seconds. So I'd like to actually compare this to something that was developed independently. The Canterbury, or now New Zealand velocity model was developed by Robin Lee for his PhD dissertation. And he used surface wave testing data, some deep boreholes, P-wave refraction data, other sources of data to try to estimate various layer boundaries within the Canterbury Basin. And this is what bedrock depth looks like across the region. Again, dark red is going to be very deep, approximately 2,800 meters below the ground surface. Near the edges of the Alps, you can see it's quite shallow, and then again near the Banks Peninsula, it starts to shallow. But one thing I'd like to call your attention to is this saddle feature running through the middle of the basin. You see it's deep here in a pocket to the north, it's deep in a pocket to the south, and then here it's shallow, roughly 15, well, relatively shallow, roughly 1,500 meters below the ground surface. And one thing I wanted to point out is with the independent psi period data set, you can kind of see this trend as well. Our deepest psi periods are up here to the north, and then down here further to the south near Rakaya. And you see that our psi periods are actually a little bit lower, roughly 4 to 5 seconds running through this saddle that we've identified in the bedrock data. We also have another impedance contrast in the Canterbury Basin, the Banks Peninsula volcanics. So the Banks Peninsula volcanics outcrop are hiding in underneath the gray layer here. And then we have the extent of what we think is the extent beneath the ground surface is highlighted by this very faint red line that I'm running my mouse across to the northwest of Christchurch. Here, I'm highlighting the psi period points that what we associate with the Banks Peninsula volcanics. Again, blue is shallow, red is deep, but in this case, the greatest psi period is about 3.5 seconds, shallower than our bedrock. What's interesting is we don't see psi period extending much further out beyond halfway through the city, and you probably have 10 kilometers of area where we're not seeing these H/V peaks. So let's try to compare this to the New Zealand velocity model. Again, as expected, shown in the middle figure, the Banks Peninsula volcanics are quite shallow near the Banks Peninsula, and then they get deep as you move away towards the north. The deepest H/V point from the Banks Peninsula is here near Pages Road. And you can see that, again, the Banks Peninsula volcanics are quite deep in this region. But perhaps to understand why we're not seeing the psi period away from the Banks Peninsula up here to the north of Christchurch, we should perhaps look at the thickness of the Banks Peninsula volcanics. Again, they're quite thick, the bright yellow colors near the Banks Peninsula, and then they peter out, tapered to zero thickness, moving north and to the west. And the reason we might not be able to actually see these psi periods is that see the Banks Peninsula volcanics in our H/V testing is that the wavelengths associated with the waves generated in our psi period are actually not able to see the relatively thin Banks Peninsula volcanics at this distance. And so we're seeing a cutoff of roughly about 150 to 200 meters thick of the Banks Peninsula volcanics. We're no longer able to see anything below that. All right. Now I'm going to start hopping into other studies that are not quite as extensive, but I figured that are worth sharing with you all. The first I'd like to highlight is in the Nelson Tasman region. This was part of Rebecca McMahon's master's thesis. She conducted surface wave testing at 29 sites, shown in the blue dots, and then she did H/V testing at 50 sites. But one thing that's really interesting about the Nelson Tasman region is we weren't actually able to clearly see a psi period estimate. We weren't able to find the phenomenal period of vibration using the H/V testing. And to try to get at this, let's look at the summary of her surface wave velocity results. So she characterized that there were 6 major deposits in the Nelson region. You have them here on the bottom left, we have the Motuary gravels and the Port Hill gravels. And these are actually generally very stiff. If you look with depth, the gravels in the Nelson region are highlighted here in red. As you go down with shear wave velocity, or go down with depth to, let's say, 35 meters per second, the Motuary gravels are as stiff as 100 meters per second, which is roughly equivalent to soft bedrock. The reason I'd like to point out that these gravels are much stiffer than what we've seen in other sedimentary basins. The green curves are coming from reference soil sites in California. The blue curves are those from Michael Deschain's master's thesis in the Canterbury Basin. And you see that the gravels in Nelson are stiff. This is because they're most likely weathered. They're weathered from the bedrock, and they might be over consolidated. If we look at some of the younger gravels, the Stoke Fan gravel and the Hope gravel, shown here in orange, they actually agree quite well with what we see from other basins. And then lastly, I would like to highlight the just the soft soils, the Tahuanui sand and the Nelson alluvium, which are near the ground surface. And here they're highlighted in purple, and they're plotting relative agreement with the interbedded sands from Christchurch and then the reference sites from Lin et al. 2014. So the reason we're not able to see this impedance contrast again in the HRV data is because the gravels are stiff and they transition from the gravels into weathered rock into bedrock, and we're not getting a strong impedance contrast needed to give us our H over V peak. All right, next I'd like to move on to Hawke's Bay. We've done a few studies here. We did surface wave testing at one site in Miami, and then last year we did H4V testing at 124 sites. Philip Girgis and I collected this data. And what I'd like to highlight in this basin is it's hard to see, so north is actually to the left, but the city of Napier is here and with a ton of blue dots. And this is where we were able to clearly identify the bedrock H/V peak. And then as we move further to the south or to the right in this figure in Hastings, we had trouble distinguishing between bedrock and maybe a different impedance contrast. So let's look at our shear wave velocity profile from the Miami surface wave testing to try to explain this. On the right, we have our zoomed in, relatively shallow shear wave velocity profile. We have near the ground surface, soft soils, and then we get into something a little bit stiffer, probably gravels as identified in irrigation logs from the farm. But if we go a little bit deeper, at about 100 meters, we have a strong impedance contrast, jumping from 300 meters per second up to about 700, 800 meters per second. And then we have another stiff impedance contrast we're associating with bedrock. At about 500 meters, the shear wave velocity increases to 1,500 or so meters per second. And this is perhaps why we weren't able to clearly identify the peaks as we move away from the city of Napier. So for now, I'm just going to focus on Napier itself. North is actually pointing up this time, as you would expect. And if you're familiar with the city of Napier, there is a big rock outcrop in the middle of the city, the Bluff Hill. And then the CBD of Napier itself is a little bit further to the south, indicated by these many points. Also, as you move further to the west, you hit the foothills of a mountain range on the west side of Hawke's Bay itself. And what I'd like to highlight again is that the psi period is going to be our rough proxy for bedrock depth. So near the, as you would expect, near the bluff outcrop, the psi period is quite shallow, around 0.1 to 0.6 seconds. And as you move away further to the south towards Miami right here, we get psi periods increasing up to 2.2. This is relatively shallow compared to the Canterbury Basin, but still quite deep. Again, we're also getting deeper psi periods up to the north in the Bayview area. So what does this mean for actual engineers? Well, we can take this data and apply the NZ, the New Zealand building standard, and we can classify the soils just according to psi class, just according to psi period. So psi class C are these soft soil sites, psi periods less than 0.6 seconds. And you'll see that the majority of near the Bluff Hill, the psi period is psi class C. But perhaps what's more important for seismic design in the Napier region is the majority of the CBD itself is actually psi class D. And this would necessitate designing more robust buildings to withstand amplified ground shaking. All right, I have two more sedimentary basins to talk about, and then I'll wrap things up. Quickly, I'm just going to highlight the Hauraki Basin, where a master's student at the University of Auckland, Zaid Rana, and I collected H4V at 99 sites. In this case, the sedimentary basin is quite deep. Our maximum psi period is about 6.5 seconds. The north is running to the left, and what I'd like to highlight is that we're actually able to see a graben structure associated with the Karapehi Fault, these red lines that run through the middle of the basin. So to the at the top of the figure, we have shallow psi periods associated with bedrock or with the rock outcrops. And again, on the edge of the basin, we see shallow to the west at the bottom of the figure. But then in the middle of the basin, we're seeing something quite interesting. We're having two zones of very deep psi period. Up here to the west, to the east, near the city of Thames and Pairoa, we have very deep side period. But as we move further to the west, we run into the Carapae Fault, and the soils are actually relatively shallow. You can see we have side periods as shallow as 0.5 or so, indicating again that site class C. But then as we move a little bit further to the west, again, we get a deeper zone where side periods again increase to about 6.5. And what's cool is this lets us get a quick overview of bedrock within the basin. The last thing I'd like to highlight is the Waikato Basin. Soko Jiang and a few of his students have been doing HRV testing around the city of Hamilton itself. And again, as you expect around the edges of the sedimentary basin where you hit rock, you have side periods that are quite shallow. A unique feature that's been identified by this HRV data is that we see a deep zone. Here's the city of Hamilton, and just to the northwest of it, we have this deepening of the sedimentary basin running from the southwest to the northeast. And so this data is, or this study is ongoing. Soko and his student collected surface wave data at a site. They wrapped up their testing actually in January, and Ashley's Cave, the student, is still processing the data. We hope to have some outcomes soon. So in summary, I'd just like to highlight that we've been carrying out regional site characterization studies all over the country, characterizing those jelly bowls. We have had extensive, robust studies, such as those in the Canterbury Basin, and we've had simpler studies where we just did HRV testing in Hauraki. What I'd like to highlight is that we can use side period to get a proxy for basement depth across an entire sedimentary basin or the country as a whole. And the other thing that we need to characterize these basins is shear wave velocity, that proxy for soil stiffness. And I think with the Nelson Tasman data, I wanted to underscore that there's differences in soils. The gravels that we saw in the Canterbury Basin were different from the gravels we saw in the Nelson Basin. And it's important to try to characterize the stiffness across the country. Each basin is actually different. What is this data actually used for? Well, we can give it to, or we can do simple site response analyses to try to understand our ground shaking. We can also input this into the complex physics-based simulations that like Flagship 1 has been carrying out over the past 5 or so years. So what's next? The easiest thing we can do is target new sedimentary basins. We can go to the Mackenzie Range where we have our hydro dams. We can go to the Manawatu-Whanganui region where you have Palmerston North and the city of Whanganui where people live and we haven't quite yet characterized. The other thing we can do is build upon existing work. For example, in Hauraki, we currently don't have a deep shear wave velocity profile measured within that basin. So we can do surface wave testing there. The other thing is this, we continue out doing this field work, it enables us to develop rapid basin models we can input into complex simulations. Again, we can use T-Naught to map bedrock, and then we can take shear wave velocity methods to develop 1 to 3D models of soil stiffness. One thing that I'm interested in is using all of this data to assess lateral changes in shear wave velocity, using tests at multiple locations, using multiple methods, and we can start to use more advanced analytical tools to take 1D shear wave velocity profiles and start looking at them in 2 or maybe 3D. And lastly, I'd like to say thank you. This is the summary of a lot of different studies. So fundings come from various sources, including QuakeCoRE, the EQC, and the United States National Science Foundation. There's been many academic staff who've worked on these studies, and there have been tens of students who I've had the privilege of working with over the past 2 years, and then also much earlier during my PhD in the States. Thank you for your time, and I'm happy to take questions.
Great, thanks for that, Andrew. Firstly, apologise to everyone. I was supposed to do the introduction, but my Zoom decided to update just as I was logging in. So any questions from anyone from the audience?
I have a question, sorry.
Go for it, Kaylee.
My question is really around the dissemination and availability of the data. I think there are a lot of geotechnical engineers in practice who are probably quite keen to learn about this stuff and probably know very little about the specifics of the work that you do, Andrew. Do you have any thoughts beyond conference papers and the academic dissemination channels, regarding getting this out there in the public?
Well, at the first level, we tend to interact with district councils to at least get permission to do this testing. That opens a door because they're honestly quite interested in trying to understand the shaking in their basins. That's the first level. At the higher level, what we're trying to do is make this data digestible by other people, and we want to actually make it freely available. So a part of my job in QuakeCoRE's Tech Platform 2 is once we have all this data, we're trying to summarize it and put it up on DesignSafe or other online portals where they can access it. So again, the site period map is something that's quite easy. You could look up where your site is in the sedimentary basin and say, oh, site period's approximately this. Maybe I should do more studies to further my results. Outside of that, I think that the shear wave velocity profiles, as we as academics try to take what's really complex and maybe simplify it, maybe we can share these shear wave velocity relationships with practitioners, help them get an idea of a basic level of ground shaking in their region. That's a hard question. We're trying to figure out how to take these academic studies and then move forward into practice. Yeah.
No, I mean, that's really helpful. It's just the sense that I can imagine showing this type of presentation to a practicing geotechnical engineer who's relying on a curve they found in a book, and them finding it to be an additional layer of information to help inform what they're doing. That's awesome. Cheers.
Thank you.
Thanks, Kaylee. Any more
Hi,
questions?
hi Liam. How are you
Go for
doing?
it, Alan.
Have you got any further with convincing the NZGD people that we need to have somewhere where we can put H over V data, or at least just the results on the NZGD? Because we're actually doing this in practice for engineers now, and providing site periods to people. So I feel like it'd be very good to have a place to put it that was available for everyone.
I can talk to this a little bit, and then Liam could probably chime in. Is a bit of troublesome bit with an NZGD is it's generally uninterpreted data, right? I mean, you're putting in borehole logs or CPT profiles. As you move into picking site periods, there's actually a little bit of interpretation on the part of the person providing the H/V curves, even more so with shear wave velocity profiles from surface wave testing. So I don't quite know how we handle that yet.
Yeah, it's a difficult one. You almost need to be actually putting the interpretations in there.
Yeah. And then the liability of what happens if someone uses my shear wave velocity profile that I've interpreted in their design and it does something. That's a tough trade-off. I think that people are still trying to figure out.
Yeah, I think you covered it off pretty well, Andrew. And that's the key thing, is nothing in the NZGD should be interpreted. So particularly with what Andrew's shown, is those if we just did an isolated test in a basin without the context of the hundreds of other tests across the basin, you can get things quite wrong. So there's a lot of time involved to actually pull all those different pieces together to say, okay, in the context of the wider study, this all makes sense. So we are in active discussion with the NZGD of a way to make this accessible, but for people not to just blindly use it.
Yeah, we've got some other data that we thought about putting in there as well, because prior to 2014, we weren't taking any GPS readings for our CPT tests. And what we thought of doing was just having a point at the center of the site and a bit of a description and maybe contact details for the company or person that carried it out, and no actual data in there. So that at least allows someone to know that there's been testing done there already.
Yeah, that's one of the avenues we've been sort of thinking about. Great, thanks for that, Alan. Any more questions?
I guess one thing I'd like to just highlight is if you're interested in this data, if you're interested in working with Liam, feel free to reach out to the two of us. We have access to this data and we're interested to see what research avenues we can go on from here. And we just don't want to be the only people with this data, so we're happy to share it.
Great. All right, well, with the excellent presentation and a couple of good questions, we've hit the 10:40 mark. So I just want to thank Andrew for a really good presentation. It's a lot of work pulling all the information of all these areas together, particularly the stuff that's happened before, during your time. So thanks very much for that, and thanks everyone for calling in. And we'll look forward to the next presentation coming up. Have a good weekend and enjoy the rest of your Friday.
Thanks, Liam.